So the standard models works very well. We can now actually do calculations to calculate the mass of the proton and the neutron and show why the neutron is a tiny bit heavier than the proton, 0.1% heavier approximately. To do that, they had to do a supercomputer calculation on this huge rack of computers here, which is sort of amazing that you need all this computational power just to simulate a single proton, right? So that's what I meant by saying that fundamental physics is about finding laws that could let you compute everything that you could possibly compute about the world in principle, right? So when you try to do it in practice, you discover that even something tiny like a proton may be really straining your capabilities of computation. But it's still, I think, an amazing achievement that we can actually do something like that, because 50 years ago, we had no idea how to calculate the mass of a proton or a neutron. Now, there's still lots of things to puzzle about in fundamental physics, and I guess three of the most famous ones are these. So why are the galaxies all rotating around faster than they should, given the mass that we can see? So the heavier a galaxy is, the more matter there is in it, the more the force of gravity would tend to pull it in, which could only be counteracted by it spinning around. And galaxies are basically spinning around as if they had 10 times as much mass in them as all the mass that we've been able to see, like stars, gas, this and that, black holes, all sorts of things. So that's called dark matter. In other words, you can solve the problem by making up some new invisible kind of matter that doesn't do anything except have this extra mass. And that actually works pretty well, that theory. I mean, there are lots of ways to test that theory is consistent, because there are lots of galaxies doing lots of different kind of things. So it's not just like a complete cop-out, the way it might sound at first. But it's frustrating to physicists because they don't know what this dark matter is. And of course, there's the possibility that there isn't any dark matter and that there's something else that we're not understanding. So that's, I'd say, one of the key questions in fundamental physics. Another one I alluded to already is that you'd expect that due to particles attracting each other due to gravity, that the expansion of the universe would slow down, just like when you throw a ball up in the air, gravity pulls it back down. But in fact, the opposite is happening. It seems that the universe is expanding faster and faster. Now, Einstein, when he made up general relativity, he came up with he noticed there was a possibility in the theory called the cosmological constant. There's like an extra term you can stick in the equation that's like a perfectly consistent, reasonable term. And it's hard to do. It's hard to tweak general relativity. But if you put that in there, then it can have the effect of making the universe expand faster and faster. He actually put it in there for some other purpose, and then he eventually decided that I shouldn't have done that. but then it turns out that that's our best explanation of why the universe is expanding faster and faster, that there's this stuff which we call dark energy just permeating perfectly evenly throughout this room and the whole galaxy that makes the universe makes things want to push out faster and faster. But that's still not completely satisfying. You'd like to know why that works that way, and so that's a big puzzle. And finally, I've been talking a little bit about gravity. That's described as best we can by general relativity, which is Einstein's theory of gravity. And then all the other forces, the forces that hold the atoms together, that hold the nuclei together, that hold the protons and neutrons together, all those are described by the Standard Model. And all those forces, by the way, are described with the help of quantum mechanics. Whereas general relativity knows nothing about quantum mechanics. So what we have is this funny situation where we have two different great theories of the universe, one of which covers gravity and one of which covers everything else, but we haven't really unified those two theories. In other words, we don't even really know how to fit those two theories together in a consistent theory. It's just luckily for us that the inconsistencies between these two theories would only manifest themselves visibly in situations that are very extreme, like black holes or something, that we have not been able to study experimentally. So it's like we've got a jigsaw puzzle and we know that it's not really fitting together yet, but we also can't find this place where it's not fitting together either. So that's a really big theoretical problem. That's not a problem like the first two. So the first two is we see something going on and we have no idea why it's going on and we're mystified. The third one is like we've got these two theories that are working great, but we don't know how to fit them together. So that third one tends to attract people who take more mathematical approach, because it's not about experimental data, it's about putting together theories. But we're stuck on all three of these, despite huge amounts of work. And so people working on fundamental physics are very frustrated right now, and they're getting very grumpy, I'd say. I mean, the peak grumpiness was about 10 years ago, but there's a limit to how long you can stay angry at something, right? So maybe we're in the post-grumpy phase of fundamental physics, sort of the depression phase. And the other thing that sort of makes it a strange situation is that nobody that I know of thinks that further progress in these type of questions in fundamental physics is going to lead to any new technology, at least not anytime soon. I mean, maybe eventually we'll be able to make black holes and smash them into each other and do all sorts of sort of godlike things that move whole galaxies around. But we're just nowhere near doing any of that kind of stuff. And so unlike the 20th century, when new advances in quantum mechanics and so on would lead to new technologies like silicon chips and lasers and the kind of laser that this laser pointer here is, we don't see anything on the horizon like that for new advances in fundamental physics. So that adds another sort of downer note to people who wanted to work on fundamental physics. So it's taken me a while to come out and say this, but I'm going to say it. Today, the most exciting physics is not fundamental physics. So if any youngster wants to go into physics, I'll say, yeah, that's a great idea, but I don't think you should go into this so-called fundamental physics, which is a very specific kind of physics. I'm going to talk about other kinds of physics. So in particular, we have the Standard Model, we have general relativity. The Standard Model is already more than what we need to describe what's going on in the particles in this room here, but we have a long way to go in using that knowledge to do things. So it's like, if you know how to play all the scales and you know how to play all sorts of chords, that doesn't mean you're done with music, right? That's the opposite, in fact. It means now you're ready to start playing some music. And so we can use our knowledge of fundamental physics to start doing interesting things, and that's what we're doing now. And we're gradually gaining what I'd call exquisite control over matter. So let me give you some examples of the kind of things that people are doing now. There are actually so many examples, I can't get anywhere near listing all of them, but I just want to list a few carefully chosen ones. So photons, okay, so photons are particles of light. And so as I said, thanks to quantum mechanics, every kind of particle is a wave, but also every kind of wave can act like a particle. Before Einstein came along, everyone thought that light was waves described by some equations called Maxwell's equations. But he said, yes, that's true, but also there's some other aspect, which is that they are also particles. The energy of waves comes in chunks. You can have one photon of red light and it will have a certain amount of energy, and you can have two photons of red light and it will have twice as much energy, but there's no way to have 1.5 photons of red light. So it comes in steps, and it's a very strange mixture of the continuous and the discrete. The waves are these wavy things, but they come in chunks too. It's hard to explain. But we know that it's true. We've done lots of experiments where you can measure photons going bing, 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 landing on a photographic plate, each individual photon making a little dot in the photographic plate. So those are photons. But the point is that this principle that every wave is a particle and vice versa doesn't just apply to light, it applies to all sorts of things. For example, sound. So if you have like a crystal, sound can go through the crystal. I'm just picking a crystal because in a crystal, the atoms are very regularly arrayed, like in a square array or hexagonal array or something. So that sound has a very simple description. It's just you've got these atoms lined up, but they can all sort of wiggle slightly from where they are. This picture is exaggerating quite a lot about how much they'd be wiggling. They wouldn't really normally wiggle that much. And as those wiggles move through the material, that's sound. But the interesting thing is quantum mechanics says that the energy in that sound comes in chunks. So actually sound, especially when you make it so precise like in a crystal, comes in particles. And these particles are called phonons. Now these are not fundamental particles. That is, they're not on the same status as electrons and quarks, but they are ways that something can wiggle, and therefore, by quantum mechanics, these wiggles come in individual chunks. And so sometimes they're called quasi-particles, but it's good to call them quasi-particles to emphasize they're like different than these fundamental particles. But in another sense, there's nothing quasi about them. You can do all sorts of things with them. You can collide them. All the things you could normally do with particles, you can do with these. So that's very interesting. People can do interesting things with sound like that. But there are lots of other things. For example, if you have a crystal, each atom will have a bunch of electrons around it in the crystal, but sometimes you could somehow knock one of those electrons off, so there'd be one atom that had an electron missing that would normally be there. And that missing electron, the absence of that electron, can move from atom to the atom. What's going on? What's going on is that one atom says, hey, I have one less electron than I want to have. And it could reach over and grab an electron from another atom. So what's really happened is that an electron is moved over to this atom. But now this guy over here says, hey, now I don't have an extra electron. So another way to think about what happened is that the missing electron moved from here over to here. And this little 16 puzzle that you may have seen, where you're moving these little squares around with your finger, is a good example. You see that black thing there is the missing square, the thing that doesn't have a square. But as you push these squares around, that black thing will move around as if it were a thing. It's the absence of a thing, but it can move around as if it were a thing. And in crystals, that these holes really do act like particles. So in some crystals, the best way to think about electrical current is to think about electrons moving around. But in other kinds of crystals, the best way to think about what's going on when electrical current is flowing through them is actually holes moving around. In some sense, those are just two viewpoints on the same thing, but it turns out that sometimes you really want to think of the hole really acts so much like a particle that you should treat it like a particle. So transistors that we all use have, in fact, they're transistors of different kinds. Some transistors have extra electrons and some have holes, and so they're both very practical. But that's just the beginning of the fancier kind of things you can do. Because, okay, I said when you knock an electron off an atom in a crystal, then you have a missing electron, which is a hole. So that's an atom that is missing an electron. Well, electrons have a negative charge, so if you're missing an electron, then that hole actually acts like it has a positive charge. So an atom with a missing electron will be positive. So that's that blue thing in the middle there with that plus sign. That's a hole acting like it has a positive charge. But you may know that positive and negative charges attract each other. So if you have an electron around, which is that red thing, it will tend to orbit the hole because they attract each other. And they can orbit each other. And you'll notice that should remind you a little bit of an atom, because an atom is a positively charged proton with a negatively charged electron orbiting it. Well, this is just like that in the sense that you have a negatively charged thing orbiting a positively charged thing, except the positively charged thing is a more funny kind of thing, right? Because it's a missing electron. But the combination acts like a little mini atom, and it can move around. So it's a particle of some sort, and that particle is called an exciton, because what's really happened is if you had an electron that was sitting in that atom in the middle there, and you knocked it off, and now it's that red guy sort of waiting to fall back into the hole, but temporarily orbiting it. But it acts like a particle called an exciton, that is